In the last section, we discussed the exponential function. The exponential function was the function exp, that its domain is all real numbers. It gives you back only positive real numbers. And it was a function with the amazing property that it is its own derivative, so that x prime of x is the same as exp of x. And in fact, we saw that this property, combined with the fact that exp 0 equals 1, completely characterizes the exponential function. We actually define the exponential function as the limit of a collection of polynomials. I won't use this today, but we actually define the exponential function this way. And from this, we derived a bunch of properties, including that exp is its own derivative. We saw that, in fact, exp of x is e to the x. That if you let where e is exp of 1, which is approximately 2.718. The fact that exp of x is e to the x, well, we can actually prove that when x is rational. And then if you already are familiar with raising bases to positive bases to arbitrary real powers, then believe that that's a continuous operation, then that proves that these two are equal. For us, we're taking this slightly slick way of defining what it means to raise a positive base to an irrational power. We're going to define, I'm defining e to the x to mean exp of x when x is irrational. There's a small technical point. If it doesn't bother you to talk about e raised to the x, fine. It's e to the x. The graph of the exponential function, we looked at the graph. It looks like this. The function is strictly increasing. The graph is concave up. That follows from the fact that the first derivative of exp is exp, but exp is always, the exponential function is always positive. So the first derivative is positive. All the derivatives of the exponential function are the exponential function. So all the derivatives are positive, including the second derivative, so that the graph has to be concave up, and you see that the function is strictly increasing. In particular, since the function is strictly increasing, it is 1-to-1. Or looking at the graph, you could say that it passes a horizontal line test. Any horizontal line hits the graph at most once. Well, this is what we need. We need for the function to be 1-to-1 for it to have an inverse. So it is 1-to-1, and we define the inverse function, the definition, the natural logarithm. Ln, it's going to be the inverse function of, well, I'll just write that. It's the inverse function of the exponential function. So that means that is not raising to the -1 power. That is, actually, let me write this down here. That is the inverse function. So Ln is the inverse function of the exponential function. So the range of the exponential function was the positive reals, so that's the domain of its inverse. And its range is the domain of the exponential function. So it goes from the positive reals and can give you back any real number at all. This is also written, since we have exp of x is e to the x, it's also true that natural logarithm is the same as the log base e. That is, it's the function that undoes raising e to powers. So because they're inverse functions, raising e to the x, so I'll start saying raising e to the x instead of exp of x, we get that ln of e to the x equals x. This is for all x, for all real numbers x. And e to the ln of x equals x for all x's that this makes sense for, so for all positive x's. The graph of the exponential function, because we know the graph of the exponential function, the graph of natural logarithm, because we know the graph of the exponential function, and the natural logarithm is the inverse of that, we immediately know the graph of the natural logarithm function. The graph, I'll draw it again, the graph of the exponential function looks roughly like this. This is y equals e to the x. How do you get the graph of the inverse function? You draw the line y equals x, and then you flip this around here. You switch, you put the x-axis where the y-axis is, the y-axis where the x-axis is, so you kind of grab this along this line and twirl it. You get this graph. So here's the graph of y equals ln of x. Oh, by the way, I should have said as a fun fact, it's natural logarithm. Why is it abbreviated ln if it looks like it should be nl? Well, because it wasn't first discussed in English. In the Latin, it's something like logarithmus naturalis, and that's why it's abbreviated this way. What do we see from the graph? We see that this function better be, we're going to write a formula for the derivative, but we see that it should be strictly increasing. So we expect the first derivative to be positive. We see that the graph is concave down, so the second derivative better be negative, unlike the second derivative here. What else do we see? We see that as x approaches 0 from the right, ln of x approaches negative infinity. That's as the x values are getting closer and closer to 0 from the right, the corresponding y values are getting arbitrarily negative. So as x approaches 0 from the right, natural log approaches negative infinity. As x approaches infinity, natural log of x approaches infinity. It does it fairly slowly, but it also approaches infinity. And certainly the natural log of 1 is 0. Okay, natural log is a logarithm, so it has all the algebraic properties that you're used to from logarithms. We could prove these from the derivative formulas in a similar way that we proved some of the algebraic properties of e from its derivative, by knowing that it's its own derivative. I won't do that, but we could, and it's certainly in the book. But let me just go ahead and say that the big two or three algebra properties we care about for all a and x greater than 0, the natural log of the product is the sum of the natural logs, and the natural log of the quotient is the difference of the natural logs. As a special case of this, you could pick a to be 1, and you'd have the natural log of 1 over x equals the natural log of 1 minus the natural log of x, but the natural log of 1 is 0. So as a special case of this, it's worth kind of knowing in and of itself that this part, you have the natural log of 1, that's 0, so it's minus the natural log of x. And then there's for all x and for all, I'm going to say for all rational numbers y, r, the natural log of x to the r is r times the natural log of x. The natural log of something raised to an exponent, the exponent comes out as multiplication. These are properties that you should be familiar with from logarithm. The only reason I've got rational powers here is because here's x raised to this exponent, and I am still not assuming, technically, that we know what it means to raise an arbitrary base to an irrational number. If however, that doesn't bother you, yes, it will be true when we've defined arbitrary bases, or arbitrary positive bases to arbitrary positive powers, that you could put any number there, not just a rational number, and it would come out as multiplication. Okay, we'd like a derivative formula for the natural log. So, but we had a formula that told us the derivative of any inverse function. We had a formula that said the derivative of f inverse of x is 1 over the derivative of f applied to f inverse of x, assuming that this denominator is not 0. So if f prime of f inverse of x is unequal to 0. We had this. What does this tell us now? All right, we want to apply this to the case where f is the exponential function, so that f inverse is natural log. Then what does this give us? We get that the natural log, so the derivative of the natural log of x, is 1 over. This is exp. F is exp, so exp prime applied to f inverse of x. Well, f inverse is natural log of x. But the derivative of exp is exp. And so you get 1 over exp of ln of x. But exp of ln of x, these are inverse functions. That's just x back again. This is 1 over x. And so this is the formula for the derivative of natural log. For all x greater than 0, which is the domain of natural log, the derivative of natural log of x is 1 over x. So do we see, for instance, that we saw the graph of natural log. Can we tell now from the derivative? Does the graph agree with the derivative? We saw that from the graph that ln of x should be increasing and that its graph should be concave down. Why is that true? So the graph of natural log. Well, we just saw that the derivative of natural log of x is 1 over x. And this is only for x greater than 0. Well, if x is greater than 0, 1 over x is greater than 0. So yes, the first derivative is greater than 0. Natural log is strictly increasing. And then what's the second derivative of natural log? Well, it's the derivative of the derivative. So it's the derivative of 1 over x. But we know how to differentiate that by the power rule. The derivative of x to the minus 1, you bring the minus 1 down, you subtract 1 from the exponent, minus x to the minus 2. So that's minus 1 over x squared. Well, x squared is always greater than or equal to 0, and we've got minus that, so this is always negative. So yeah, the graph should be concave down, and the function is strictly increasing. Of course, we can combine our new derivative formula with our other formulas and combine it with the product rule and the chain rule and the quotient rule. So let's do a couple of examples. Actually, let's do 3 examples. So here's one example. Let's calculate, let g of x be x times the natural log of x minus x. Of course, the domain of this we're using as the domain x is greater than 0 so that this part is defined. But assuming x is greater than 0, what's g prime of x? Here, this is the product of two functions of x. So the derivative, the first thing times the derivative of the second, plus the second thing times the derivative of the first. That's the product rule. And then you subtract the derivative of x. Okay. This is x times the derivative of ln of x, 1 over x. That's our new rule. Plus the natural log of x times 1, and then minus 1. But x times 1 over x is 1. Plus the natural log of x minus 1. The 1's cancel, and you get the natural log of x. So this is a function. X ln of x minus x is a function whose derivative is ln of x. So we say that this thing itself, this isn't something whose derivative is ln of x. This is an antiderivative of ln of x. All that means is it's something whose derivative is ln of x. Okay. Let's look at something involving the chain rule. So let's, another example. Let's look at m of x equals the natural log of negative x. Now you might be saying to yourself, self? That's not defined because the domain of natural log is only the positive real numbers, and look, there's a minus sign. Well, we just need for minus x to be positive, which means we need for x to be negative. So this is for all x less than 0. So the domain of this function is the x values less than 0. Okay, so that negative x is a positive number, and you can take natural log of it. We can apply the chain rule. What is m prime of x? You take the derivative of the outside function, natural log. So that's 1 over, and then you leave the inside stuff the way it was. So you get the derivative of the outside function, leaving the inside stuff the way it was. But then you have to multiply, the chain rule says you have to multiply that times the derivative of the inside function. This is minus 1 over x times a minus 1. This is 1 over x. So this function also has derivative 1 over x, just like natural log itself. So these two functions, natural log of x and natural log of negative x, look like they have the same derivatives. And you might, they're both 1 over x. And you might be tempted to say, aha, we had an earlier result that said if two functions had the same derivative, they differ by a constant. So is it true, you might be asking yourself, is it true that the natural log of negative x equals, so this is a question, is it true that this is the natural log of x plus some constant? And the answer is absolutely not. Right? These functions don't have the same domains. This function's domain is the x is less than 0. This function's domain is the x is greater than 0. The theorem said, yes, if two functions are defined on the same interval and have the same derivative on that interval, then they differ by a constant on that interval. But these two functions aren't defined on the same interval. One's defined where x is positive, one's defined where x is negative. This is absolutely, utterly, totally false. But, you know, we would kind of like to have one formula that tells us, oh, okay, when x is positive, the derivative of natural log of x is 1 over x, and when x is negative, the derivative of negative x, or the derivative of natural log of negative x, is also 1 over x. Well, there is a nice way to do that with one formula, and it uses absolute value. the general formula that includes both cases, I claim it's this. Then the derivative of the natural log of the absolute value of x is 1 over x. And this is for all x except 0. Why is this right? Absolute values bother people quite a bit. Why is this right? The absolute value of x, it is the function that is, well, if x is positive, the absolute value of x is just x. Or even if x is 0, that's true. If x is negative, the absolute value of x is negative x, because if x is negative, like x is negative 5, then this would be negative negative 5, so it would be plus 5. So this bothers people. The absolute value of x is negative x. Wait, the absolute value is supposed to be positive. Yes, and if x is a negative number, negative x is a positive number. So this is what the absolute value function does. And so what this says is if x is negative, the absolute value of x is negative x, and then the derivative is 1 over x. That's what we just saw. And if x is positive, this would say the derivative of natural log of x is 1 over x, which is our formula for the derivative of natural log. So this one formula gives us both our normal derivative of natural log of x formula, if x is positive, and it gives us this other derivative formula. The derivative of the natural log of negative x is 1 over x if x is negative. Okay, let's look at another example, but a physical example. So let's look at example, an object of constant mass m is moving in a straight line through some fluid. So, it might be something moving through air or through water or through oil, through some very viscous fluid, through some fluid. Suppose that B and V naught are positive constants, so are positive constants. And that and x naught is a constant, but not necessarily positive. And another and that the position x as a function of the time t, the position as a function of the time t is given by x equals 1 over b times the natural log of b naught t plus 1 plus x naught. Okay, there's the statement. What's the question? The question, or the command, I guess I won't ask a question. The imperative is show that the sum of the forces, in fact I should have said this. I'm going to assume that there's only one force acting on the object. So maybe I should write that. Assume that the only force acting on the object is the force of resistance. All right. So, right, this object is moving through this fluid, and the fluid pushes back, kind of with friction there. You know, it's like a friction force. As the object moves this way through the fluid pushes back to oppose the motion of the object. We're assuming that's the only force acting on the mass. So either we're in space, in outer space, but still with a fluid, so maybe we're doing this on the space shuttle or something. Or we're talking about horizontal motion, and we're only talking about the horizontal position, and so vertical forces like gravity don't matter. One way or the other, we're going to assume that the only force acting on the mass is the force of resistance. Now, let's try stating what we want to show. Show the force of resistance is proportional to the velocity squared so proportional to the square of the velocity of the object. Of the object. And acts in the direction that opposes the motion. In the direction, so opposite the motion. And while we're at it, also show that the v naught that I just said was some constant, show that v naught is the initial velocity. So is the velocity at time 0. The velocity of the object is the velocity at t equals 0. And x naught is the position at time 0. All right. Well, 2 boards worth of stating the problem. All right. So first of all, for what t's do I mean this is true? Well, the t's for which it makes sense, we need to take natural log of positive numbers, so we need t to be greater than -1 over b v naught. B and v naught are positive, so this is a negative number. So this includes a time, this also includes time 0, which is good. So, all right, let's look at this. Of course, we use Newton's second law of motion, which says the sum of the forces acting on the object is the mass times the acceleration. So, Newton's second law for something with constant mass, Newton's second law of motion. We're assuming the sum of the forces, well, we're assuming it's just the force of resistance. I said the only force acting on the object is the force of resistance. And that is, for a constant mass, that should be the mass times the acceleration. And so what we'd like to show is the mass times the acceleration. If we're trying to show the force is proportional to the velocity squared, then the force is the mass times the acceleration. We need to show the mass times the acceleration is proportional to the velocity squared. But m is a constant, so saying that the mass times the acceleration is proportional to velocity squared, so equals a constant times the velocity squared, is the same as saying the acceleration equals a constant times the velocity squared. So we need to find the acceleration of the object, which is the second derivative of the position. Of course, we also need to compare it with the velocity squared, so we have to find the velocity. But we have to find the velocity to find the acceleration anyway, because the first derivative of the position is the velocity. So let me write this formula again up here, and then we'll start looking at it. So you've got this. All right. First, let's just, if x is given by this, when t is 0, it's easy to see what happens. When t equals 0, over here we get the value of x when t is 0. That's just x at times 0. It would equal 1 over b times the natural log. If t is 0, this part's 0, that's a 1 plus x naught. But the natural log of 1 is 0, so this is 0, and so you get equals x naught. So yes, this formula, yeah, the x naught in it is the value of x at time 0. Well, that's good, because otherwise we shouldn't be denoting that constant by x naught. Let's calculate the derivative. The velocity is the instantaneous rate of change of the position with respect to time. So it is dx dt. We know how to differentiate this. This is just a constant, so you just take that constant. You multiply times the derivative of this. This is the derivative of natural log done to another function of t. So you have to use the chain rule. You take the derivative of the outside function, natural log. So the derivative of natural log is 1 over the thing. So you get 1 over, you leave the inside stuff exactly how it was. But by the chain rule, you then have to multiply times the derivative of the inside stuff. So we still have to multiply times this derivative, plus the derivative of x naught. X naught is a constant. So that's plus 0. We still have to multiply times this derivative. The derivative of this with respect to t, the derivative of the constant, 0. The derivative of a constant times t is just the constant. So we end up with 1 over b times 1 over b v naught t plus 1 times a b v naught. The b's cancel, that b and that b. And so you're left with the velocity is v naught over b v naught t plus 1. All right? So we just found the velocity is v naught over b v naught t plus 1. Okay? We're supposed to show that that constant v naught is the velocity at time 0, but now we can do that. When t equals 0, on the left, you get, well, the velocity at time 0. The velocity at time 0 is, you put in t equals 0, this part's 0, you get v naught divided by 1 equals v naught. So yes, v naught did denote the initial velocity. And again, it better, because that's what v naught's supposed to denote, the initial v value. We want to find the acceleration. The acceleration is the instantaneous rate of change of the velocity with respect to time. So it's dv dt. So this is dv dt. And so we have to calculate the derivative of v naught over b v naught t plus 1. Okay, we have a bunch of choices. We could use the quotient rule. I'd rather not. You can just pull out the v naught. It's a constant. So you get a v naught. And then rewrite the rest of it as 1 over this. Well, that's this denominator to the minus 1. So we've really got b v naught t plus 1 raised to the minus 1 power. That's what we have to take the derivative of. You get the v naught times, all right, use the chain rule. This is one function of t, and then you've done another function to that. You differentiate the outside function, raising to the minus 1 power first, leaving the inside stuff exactly how it was. So the power rule, the minus 1 comes down. You subtract 1 from the exponent, so you get minus 2. But then by the chain rule, you have to multiply times the derivative of the inside stuff. So again, times the derivative of b v naught t plus 1. So you get a v naught times minus 1 times a b v naught t plus 1 to the minus 2 times another b v naught. Okay. So what are we getting for the acceleration? So what do we get for the acceleration? We get that the acceleration, A, is, if you multiply that stuff together, you get a minus b v naught squared divided by, so rewrite the b v naught t plus 1 to the minus 2 is dividing by this. You get this, but remember, we just showed a minute ago, the velocity is v naught over v naught bt plus 1. Right? So this part is exactly the velocity squared. So what we've just shown is that a is minus b times the velocity squared. But this means that the force of resistance is m times a. So it's minus m times b times v squared. Well, this is what we were trying to show. This is all a constant. It says the force of resistance equals a constant times the velocity squared. That means the force of resistance is proportional to the velocity squared. The fact that b and m are both positive, so this is a negative constant, which means that the force of resistance acts in the negative direction. But our initial velocity was positive. It was v naught, and we assumed v naught was positive. So initially, the object is moving in the positive direction. The force of resistance is in the negative direction, as it should be. The force of resistance pushes to counteract the motion. That's what forces of resistance always do. Okay, this was a short section. We didn't do too many examples, but in the next section, we'll deal with general bases, and we'll combine some of our stuff for e to the x and some of our stuff for the natural log of x, and have logs to arbitrary bases and arbitrary bases raised to powers. It also won't be a long section, but yeah, we'll do more of this stuff in the next section.